Okay, so in the previous week and yesterday's class, we have seen the several components of the memory hierarchy, starting with the component that is farthest away from the processor, that is hard disk, then the main memory, and finally we have studied the on-chip cache in great detail. One thing I should mention is that the cache memory that we have studied basically showed a single level of cache. However, in modern microprocessors, commercially available microprocessors like the ones you have on your computers, the ones that are there on the servers, etc., most of these microprocessors are multi-core microprocessors where there are multiple identical cores on the same chip, as if you have four different CPU chips, or electronic capability of four different CPU chips is combined into one chip. In such cases, each of these cores have a private cache, which is typically called the L1 or level 1 cache. And then they have one or two levels of shared caches. Okay, larger shared cache memory, level 2, level 3 cache, etc. Okay. So the cache memory that we have studied did not have all these complexities, but later on, if you take advanced courses on computer architecture, you will be familiarized with those. So basically, that is another kind of sub memory hierarchy, you can say. That is a memory hierarchy inside the processor itself that we are not considering. Now we have considered the interaction between processor register, processor cache and main memory. Now the interaction, today's class we will study the interaction between main memory and hard disk drive. Okay, so that is a very important part of modern computers. Unless you understand this part, it will not be clear to you how are we capable of working with extremely large amounts of data and extremely large program software. Okay, so virtual memory is the technology which makes all this possible. To give you an motivational example, I think I have discussed this earlier, long back in some class. Suppose you have a computer on which you have, say, 4 GB of DRAM or main memory. Okay. Now, with that, your operating system itself is occupying, say, 1 GB out of that. Okay, about 1 GB. So you are left with, say, about 3 GB of user space where you can load your application binary and data and work. Question is, how are you being able to manage your day-to-day work with only 3 GB of main memory, given that you have extremely large program binaries and oftentimes they work on extremely large files. For example, you watch a HD movie. An HD movie file can typically be 6 GB, 8 GB, 8 GB, whatever, okay, for a 2-hour movie. How are you being able to watch a 6 GB or 8 GB movie using a movie player software that binary itself is several hundreds of megabytes? When your total available memory size is only 3 GB. So this is an important question to understand, and this is quite perplexing that how is this even possible? Well, virtual memory is and combined with something called paging is a technology that makes this possible, and in today's class we will understand some aspects of it. When you take the operating system course in the next semester, you will study this topic even in much greater detail. So there will be entire chapters dedicated on how virtual memory is actually implemented, what are the optimizations performed to make it more efficient, what are the challenges, how those challenges are overcome, how virtual memory implementation has evolved over the years, all of these aspects. The concept of virtual memory is an extension of the concept of cache memory and main memory. In cache memory and main memory, we use the cache to hold a subset of the entire data of main memory. We perform read from the cache, we perform writes to the cache, and either we immediately update the write to the lower level of main memory, or we do that is called write through, or we do not update it. We wait and we update it later on. We keep a record that it is a dirty block, and you update it later on in a write back scheme. Okay, so the virtual memory concept is similar, except that now the memory, main memory itself will be treated as if as a cache. It will hold a subset of the data that or program binary that the hard disk is holding. Okay. It is managed jointly by the CPU hardware and the operating system. First of all programs nowadays, all operating systems nowadays are they are multitasking, in a sense that you can have multiple processes running on your system at any given point of time. Running means we're not occupying your CPU. The CPU is occupied by only one process at a time, but their images are there in your memory and they are ready to execute. Okay, when their turn comes. What is a process? A process is a program in execution. We have discussed these things earlier. I will discuss it again, maybe in today's class, maybe in the next class. The programs, all of them, they share main memory, and each program gets a virtual address space holding the frequently used code and data. Frequently used code and data, not the entire, not necessarily the entire program code and data. This is a very important concept. If you write a 5-line C code and compile it into a binary, then yes, maybe the entire program would be there in main memory, where entire executable, your a.out, when you want to execute it, entire thing will be in main memory with all its local variables on the stack, all its global variables if it is there. Okay, in another portion of the virtual address space. Then if there is dynamic memory allocation, memory will be allocated. We have studied this when we studied assembly language programming and the basic memory layout. However, that is a virtual memory layout. All programs you will find they are having kind of similar virtual address space starting from a minimum value to a maximum value. Of course, multiple programs cannot occupy the same physical address. Okay, that is impossible. So what is happening is the programmer is getting an illusion that the entire address space is available to his current program that he is running. This illusion is created to the programmer by the operating system. Your entire address space, we will very soon see an example, say with 32-bit addresses, you basically have 4 gigabytes of addressable memory. You will think that I have 4 gigabytes of addressable memory to work with in my program. Actually, you do not. You are having an illusion that you have entire 4 gigabytes. Entire 4 gigabyte cannot be given to your program. Out of that entire 4 physical, if you think in a physical manner, out of those 4 gigabytes, 1 gigabyte is gone. 1 gigabyte is taken away by your OS. There are so many other applications running on your system. So if you are running something like, say, a word processing software or maybe a Microsoft PowerPoint, this type of software, they take considerably large amount of memory. These are complicated software. Okay. So you are probably actually you have to yourself only maybe a few tens of megabytes, maybe 20, 50, 100 megabyte of memory, but you are getting an illusion that you have the entire 4 gigabyte available to you. So this is a very, very useful and very, I would say almost a magical technology actually that makes modern computing possible. Now the virtual address space of every individual program is protected from other programs. Other programs are not allowed to just perform arbitrary modifications to the virtual address space of another program. How is this protection enforced? Well, there are techniques. I will not go into this. Probably when you study virtual memory in your operating system, some of those topics will be covered. Now, we have seen that data transfer between the main memory and the cache happens in chunks called blocks or cache lines. In virtual memory, the chunks are called pages. Okay, this is the technical name, page. These pages are typically they are larger than blocks, and of course they are much larger than a single word. Okay, what is the typical size of a page, a chunk? Typical size of a page is maybe say several kilobytes at least, can be several megabytes also. Okay, in fact modern computers support multi-sized pages. Okay, so on a fly the operating system can decide that for this application the nature of its data access is such that the paging this application will be more better served if the page sizes are larger, say 16 megabyte pages. And sometimes it thinks this application is such it will be better served if the page sizes are small, say 4 kilobyte pages, something like that. Of course, you need both operating system software support as well as processor hardware support, the memory management unit, to support this multiple size pages. All of these examples you will find when you study operating system, you will be exposed to. Now, what happens is so what you need to do is that you need to translate an address, virtual address, to a physical address. So look at this diagram here. Okay, suppose I have fixed size pages. For example, 4 kilobyte pages. I should maybe just write 4 kilobyte pages. So this is a 32-bit addressing system. There is an address translation mechanism which takes this 32-bit address. Because it is a 4 kilobyte page, now you consider page offsets. Earlier, when we were looking at words, 4-byte words, only 2 bits were dedicated to denote the word, and there was a 2-bit word offset. Now we are looking at substantially larger chunks called pages. So a page is a contiguous block of memory. Okay, so you look at the necessary number of bits. How many bits do I need to denote 4 kilobyte? 4 kilobyte is 2 power 12 bytes. So I require 12 bits to denote the page offset on the least significant bit side. So from bit number 0 to bit number 11 of the virtual address is your page offset. Then from bit number 12 up to bit number 31 is a virtual page number. Okay, this is not a real physical page number. Why? Because there is a translation mechanism that translates this to a physical page number. The number of physical pages is usually less available. Number of physical pages available is actually less than the number of virtual pages shown. Here in this case, how many virtual pages are being shown? 2 power 20 virtual pages are being shown. Okay, but there are only how many physical pages are available? There are, first of all, only 30-bit effective address physical addresses are available. Okay, So there are only 2 power 30 amount of addressable memory, 2 power 30 bytes of addressable memory, of which 12 bytes denote the page offset. So the page offset remains the same, and the remaining 2 power 18 physical pages of size, each of size 2 power 12 bytes, denote the physical page number. So there is a translation from a virtual page number to a physical page number. How does this translation happens? There are mechanisms. We will study that in the later part of today's class. Okay, now, some of these address translation, when the address translation happens, the physical and it gets the physical address, some of these pages are actually there in memory, in main memory. So it's a successful translation. However, some of these address pages are physical addresses actually correspond to addresses on the disk. Those pages are not there in memory yet. This situation where a translation actually misses, so this is called a physical address translation miss. This type of an address translation miss is called a fault. In cache memory, a miss is a cache miss, and cache miss takes about few hundreds of clock cycles to handle. This is called a page fault, on the other hand, where the necessary page is not there in the main memory. So here this physical address, whatever is shown, is actually in the main memory. Okay, it is expected, it would have been ideal that I have found the page in main memory. However, address translation points to a location on the disk that shows that the page is currently not there on main memory. Then it is a page fault. It is called a fault. It is not really a programming error or anything to do with the erroneous programming, but it is quite serious. The reason why it is quite serious is that to handle the absence of a page in your RAM, where the page has to be brought from main memory to the RAM, this handling takes millions to crores of clock cycles. Okay, so in the order of 10 to the power 7 clock cycles to handle. Why? Because the main memory operates substantially faster than the hard disk. The hard disk is quite slow in operation, as we have studied. Okay, there is a lot of latency, and it's an electromechanical device. It can never compete with a pure semiconductor memory in speed. So if your DRAM is operating at say 500 gigahertz clock speed, I mean, it is nowhere compared to a 500 gigahertz clock speed. It is operating at a orders of magnitude slower rate. So this translation, fetching of data from disk to main memory, and then it will go from main memory to the cache. Remember again, rule 101 of computer architecture. The CPU does not access the hard disk drive directly. The CPU does not care about the hard disk drive. It does not depend on the hard disk drive. It depends only on main memory. Its only assumption is with respect to main memory. Okay, that yes, a main memory it expects that will be present. And hard disk drive is classified as an input-output device, which at first, when you first hear it, it sounds strange that we cannot think of any modern computer which does not have a hard disk drive. It's an indispensable part of any modern computer, but in computer science technology, a hard disk drive is an optional IO device. I mean, there are computers, it is possible. I have personally worked with computers which did not have any hard disk drive, only main memory, which means you cannot save any file as such on it intentionally. Because of security reasons, you cannot download anything, you cannot save a file. All these issues are there, but intentionally that those computers have been designed in that way. That's why it was like that. Okay, so this page fault is handled by an interrupt mechanism, and the process is set into a waiting state, and then finally when the page is available again, the process is loaded to the CPU and it works with it, etc., etc. We will discuss it again. I have discussed it already once, but we will discuss it again maybe in later class. Okay. So the moral of the story is the amount of virtual space available is not really the real representation of the amount of physical space available. For example, in the diagram shown above, because you have 32-bit virtual addresses, the virtual memory size is 4 GB. 2 power 32 is 4 GB basically. 2 power 32 bytes. However, if you look at the physical pages, it is 1/4 of that address because the MSB2 bits are not present. It's only a 30-bit physical address. So physical memory size is 1 GB. In 64-bit machines, 48-bit virtual address is very, very common. Okay. Not only in, I don't think not only in 64-bit machines, I think in 32-bit machines also. 48-bit virtual addresses are quite common, and as you can guess, 48-bit virtual addresses, in any case, it doesn't, I mean, you cannot hold on a 32-bit machine. So the addresses of variables that you can print, say in a C program, there is an integer I, and you can print its address, I think with the %p format specifier using a printf statement, and you can write %i. Those addresses that you are printing, those are virtual addresses. Okay, the programmers never know in general what is the physical address that they are working with, and we are absolutely fine with it. We can still keep on working given this fact that every process has a separate virtual address space. This is a very important concept to understand. That's why I'm repeatedly stating it. Every process has a parallel separate address space, okay, which gives you an illusion that the entire address space is available to only one single process, the process that you are currently working with. However, that is not the physical reality. That is not possible. Okay. Now what happens when a page fault happens? On page fault, the page must be fetched from disk. It takes millions of clock cycles. It is handled by operating system code. So it is extremely important that page fault rate is minimized. Okay. What do you mean by minimized page fault rate? We have seen it is better if the cache hit ratio is maximized or cache miss rate is minimized. Exactly similar concept. Page fault rate should be minimized. The only thing is that page fault rate should be minimized even more aggressively. Okay. Why is it more important to minimize page fault rate than say cache? I mean, of course, cache miss rate is also very important to minimize. But why do you think it is? If I claim that, say, if you are happy with 95% cache hit rate, you would not be happy with anything less than 99.99% page hit rate or page fault rate of less than 0.01%. Why is that? Any student has any answer? Anybody? Students? Not a very difficult question. Hello, can you hear me?
Yes, sir. Yes.
Yeah, so my question is, say I want to minimize both cache miss rate as well as page fault rate. Okay, that is any good computer system should have low values for this. However, usually you will find that people are happy, very happy if the cache miss rate is something like less than 2%, less than 3%, etc. Whereas they would only be happy with a page fault rate which is less than 0.01% or something like that. Why? Why is it more important to?
Page fault goes to hard drive to access to memory.
Yes.
And cache fault goes to main memory.
Okay. So
Since main memory is faster than hard drive, so we are satisfied
yeah,
with the low.
exactly. So the impact of a cache miss is, we have seen calculations of average memory access time or the AMAT metric. Impact of the cache miss can be quite bad, substantial, but the impact of a page fault on the process is disastrous basically, because the process is sent to an wait state. It is evicted from the processor, sent to a wait state by the operating system, and then again after some amount of time, when the page has been fetched from the hard disk to the main memory, it gets an opportunity to come back to the processor. So because we are dealing with millions to crores of clock cycles, tens of millions of clock cycles penalty, okay, we have to be very, very careful about how much page fault rate is actually happening in the system. If the page fault rate is even slightly high, okay, not even full 1%, like it is getting close to 0.1% or so, okay, I mean the performance impact can be disastrous. In fact, I remember in operating system, there are some calculations that you can do to show that if, with reasonable assumptions, if your page fault rate is anything more than 1 in 10 power 6, which is 10 to the power minus 6, then your system performance is really bad. 10 to the power minus 6 is 0.0001%. If it is page fault rate is more than that, then your system performance will be really bad, something like that. So minimizing page fault is very important. Primarily two techniques are applied. One is, first of all, there is no associativity maintained in main memory, okay, and hard disk. It's fully associative. Anywhere in main memory, any page can come and sit. Anywhere means, well, there are some locations of main memory where maybe some portions are kind of not made available to any user process. So any user process pages might not come here, but in general, if you look at the main memory, anywhere, any available space is there, the page can come and sit. And because pages are of different sizes, that creates further problems, because you need to find a hole or an available space in the main memory where that page can come and sit in. You understand? The pages now are of different sizes. It is possible. All the pages are not of the same size. So this creates a problem that you need to first of all find a hole in the main memory where the page has to come and sit in. Suppose in your main memory, you have total amount of free available space is 20 megabyte, but this 20 megabyte available space is not contiguously available. It is available in chunks of 2 megabyte, 2 megabyte, 5 megabyte, something like that. Now you require a page of 10 megabyte to come and sit. Page is a contiguous block of data, okay, data or binary, whatever. It needs to come and sit in main memory. But there is no 10 megabyte size space, although the total space is available. In main memory, it exceeds 10 megabyte. There is no single 10 megabyte contiguous space where a 10 megabyte page and comment sit. This problem is called a fragmentation, and there are again techniques how can you solve fragmentation problems, etc., etc. Okay, so I'll not go into all of this, but a fully associative placement helps in general. You allow any page to sit anywhere in memory, and the replacement algorithms, once you bring a page inside the main memory, unless you are absolutely sure that this page must be, or you are forced that this page must be evicted, do not evict that page. Because evicting you evict a page, then again you need to bring in that page from hard disk. That is it's a horrible thing. The process of continuously bringing in a page from hard disk to main memory, then sending out that page from main memory to hard disk is called swapping. Okay, there is a space on the hard disk dedicated where recently swapped out pages are kept. That part of the hard disk is typically the access is faster than the rest of the hard disk. Okay, why are they kept in swap space for some time with the expectation that this page has just been evicted and it might happen that again it might be called back. Remember when you were watching at direct mapped caches, there were these capacity means that one page is being brought in immediately, it is being sent out because there is no other place. There is not sufficient space in the cache, and again after some time, a short amount of time, again it is being brought in, again it is being kicked out. Repeatedly, this thing happening in cache is bad. We have already discussed this, and we went ahead with associative memory, associative cache, fully associative cache, etc. However, this thing happening in main memory is disastrous because every swapping out and swapping in, every page fault is millions of clock cycles. So you don't really want that. Okay. So your page replacement algorithms of which page that is there that should be replaced by some other page must be really, really smart. Now, to perform, we have seen some abstract translation mechanism. What is this translation mechanism? How is it performed? Now we will study. The translation mechanism is performed using a data structure called a page table. What is the page table? It is an array of page table entries which is indexed by a virtual page number. The index of this array is a virtual page number. The page table register in CPU points to the page table in physical memory. So it looks something like this. There is a page table register in CPU. That is a dedicated register. We have not discussed this register till now. Now you are learning about one more register. Okay. This register can only be set by the operating system kernel. It is not user modifiable. Okay. This is a very important piece of information, this page table register, and because of security reasons, you cannot allow untrusted user processes to make arbitrary changes to the page table register. Only the operating system kernel in a kernel mode of operation can possibly do this type of changes. This two-dimensional this array with the different rows, this is actually the page table. How does the page table work? Well, it has rows. If the row index is a 20-bit virtual page number in this case, because you have decided that my page offset is 4 kilobytes, so maybe I can again mention that in this case the page size is 4 kilobyte. Page size is not guaranteed to be 4 kilobyte all the time. In this case, it is 4 kilobyte. Fine. So you have a 12-bit page offset. Then you have a 20-bit virtual page number. With this 20-bit index, you go into the page table. So how many rows are there in the page table? Students, how many rows are there in the page table? Come on, hello. Are you there?
Yes, sir. Yes, sir.
Okay, how many rows are there in the page table? The virtual page number is the index of this page table. So how many rows are there?
The 2 power 20.
Right. So about 1 million rows are there in this page table. Then what is the content of the page table? The content of the page table is 18-bit physical page number, because there is this is the table that performs this translation. The scheme is really simple. Okay. So it contains a 18-bit physical page number. The page offset is directly copied from the virtual page offset. And to get the physical address, you look at the 18-bit entry corresponding to that virtual address index in the page table, concatenate with the page offset, and you get your physical address. There is one catch. The catch is that every row also contains a single bit called a valid bit, which if it is 1, it shows that the page table entry can be the page table entry can be trusted. It is an actual physical page number where the page is there in main memory. If it is not there, if the bit is 0, that means the page is not there in main memory. It is there in hard disk, and it is a page fault. So if this points to, if the virtual page number points to a row where there is a physical page number, some entry is present, but the valid bit is 0, the mechanism declares a page fault. Okay, it is a page fault, and then there is an additional mechanism of how to search for that page on the hard disk and how to fetch it from the hard disk, etc., etc. That mechanism gets invoked, and then that page is restored. The page table is updated to show that yes, now this is a valid page. The page table, the physical page number is updated when the physical page resides on main memory, and then it again that process is brought into the CPU. Then that page is probably block of it is brought into the cache. Maybe there is at that time there is a mandatory or compulsory miss, but finally the portion of the data that the CPU needs is brought in the cache. From there it is brought in the registers, and then the CPU proceeds. So all these steps complete. Okay. So because when the valid bit is 0, it is actually looking at an address to the disk. Okay. Now this shaded rows directly pointing to disk is it is not. Well, there are some additional steps in this, because disk addresses again have to be calculated. It is not that directly easy. There is also another mechanism which calculates this. I'll not go into that thing because some complications are there. But essentially, this is a simplistic diagram of what is the role played by a page table. A page table is a very important piece of information where by indexing the virtual using the virtual page number as an index, you find out the physical page number. So here physical memory means the DRAM, okay, the actual available DRAM, and from there you can get. Now the question is, how will you perform?
Excuse me, sir.
Yes, yes.
I have a query that in the page table, the number of entries is 2 power 20, whereas the content is, since it is an 18-bit content, so it is 2 power 18. So will there not be any repetitions?
The page entries will not all be valid physical memory entries, address entries, because the number of possible physical memory arrows going from the page table to the physical memory is limited to 2 power 18, right? So the remaining pages must be pointing to somewhere in the disk.
Okay.
Okay.
Yes, sir.
Acha. Before we go to the replacement policies and other things, I have two questions because this diagram is good. Let me first state these questions, get answers from you, clarify a little bit, then we will move on. Do you see any problem with this concept of page table? First of all, what is the size of the page table? 2 power 20 in this case, right? Is the page table unique to the process or it is unique to the entire memory module? Means every process will have its own page table, or there will only be one page table for your entire computing system, entire computer at any given point of time? Anybody has any answer? Acha, is the virtual page number unique to your process, or it is unique, or it can be the same for different processes also? Means currently say the virtual page number is 10,000 and it is pointing to the 10,000th row of the page table from where an address translation is happening. Is a 10,000 virtual page number allowed in another process? Say process A is having a virtual page number 10,000. Is a virtual page number 10,000 allowed in process B also? Yes or no?
No, sir.
No. Why no? Because just a few minutes back, I mentioned that every process has an entire virtual address space available to it, where it has an illusion that it has the entire virtual address space starting from 0 up to the maximum available. So why can't process B have another virtual page number of 10,000? What is the problem? Any process can have a virtual page number of 10,000. Okay, every process can have a virtual page number 10,000. That 10,000 doesn't mean anything physically. It is just an illusion to that process and the user using that process. Using the page table, you perform a translation for what is the meaning of 10,000 in the context of this process. For this process, what is the physical page corresponding to virtual page number 10,000? That you have to find out. So this virtual page number shown, that can be 10,000 for process A, process B, process C, anything. Which means that this mapping here, if this virtual page number is 10,000 for process A, this mapping is valid only for process A. For another process A, B, this mapping will be something completely different, because it is not pointing to the same physical page. It might point to the same physical page by chance, but the chance of that happening, probability of that happening is very less. There can be shared pages in memory by different processes. Absolutely possible. That creates further problems because, well, we won't go into that, but shared pages are possible. But the chance of that happening is less, which means every process has a unique page table for it. Now think about it. This page table is a non-negligible sized data structure. Okay, it has more than 1 million rows. Every row has a 18-bit address. Along with that, a valid bit, 19 bits. 19 bits is like about 2.5 bytes. 1 million such rows. Okay, which is over 2.2 and over 2.5 megabytes just for to hold the page table for this process. And the process itself might not be, the entire binary might not be 2.5 megabyte. 2.5 megabyte is not a small amount of data a small amount of data or small amount of binary. Okay, if you compile a C program, most of the times the type of C programs you use, their size that even if you write very large C programs in your assignments, a few kilobytes or tens of kilobytes. 2.5 megabytes is a full-fledged software app. Okay, here just to hold the information of this address translation information, you have a over 2.5 megabyte overhead for every process. That's a problem. Okay, that's a huge problem. So we will see how to solve this problem partially in the next slides, but to get a full idea of, there several techniques are applied to solve this problem. We will study only one hardware based technique to solve this problem, but there are many other optimizations are performed by operating system kernels of how to design and hold page tables. That's a topic in itself. How to optimally design and hold page tables. Page tables might not necessarily be of this simple structure. They might, because of reasons of optimization, they might be more complicated. Logically, this is what it does. It looks at a virtual page number, indexes into an array, reads the entry of that row to get the physical page number. If the valid bit is 0, it understands that it is not in memory. It declares a page fault and brings the necessary page from disk to main memory. This is what a page table, this is a role that page table plays. Logically, this is correct, but the representation shown here in this diagram is oversimplified. It's not that simple, because just the size of the page table can be quite a big problem actually if there are many processes running on your system. Secondly, where is the page table stored? Page table itself is like, as I said, like say, I mean, it takes over 2.5, in this case, over 2.5 megabytes of space. Where will you store it?
In the main memory.
In the main memory, correct. Okay. So what is the meaning of storing a page table in main memory? For a process, you, first of all, your CPU generates virtual addresses. Okay. This is generated by the CPU program. CPU. You go to the page table to calculate get its physical address. Every memory access performs the same translation, right? And your page table is in main memory. That means to fetch something that is there in main memory, you have to first consult another thing in main memory. So it's an additional extra memory access over it. Till now, we are repeatedly beating this drum. Memory access is slow, von Neumann bottleneck, this, that from the beginning of the course. Just to get data, just to know where the data is in main memory, I first must go to the main memory. That sounds, I mean, really stupid, right? I mean, it doesn't make much sense. So, any suggested solution? What can we do? Any suggestions, students, based on what has been taught in this chapter till today? Common sense solution. What did you do when memory access became slow? We said, well, I understand memory access is slow. I cannot do much because the physical electronics part of it is not in my hand. The fact that electrical signals going out of CPUs are slower than, like, any signal going outside a chip becomes slower and the memory cannot operate at similar clock speed as the CPU. These are things which I cannot control. But what I can do is I can build a small, fast memory inside the CPU chip itself, which will hold part of the program and data that the memory is holding, which are relevant to my process that is currently being executed by the CPU. And I'll be happy with this most of the times because there is this principle of locality at place, both spatial locality and temporal locality. So once I bring in a block from main memory to cache, I'll be happy with playing with that block for some amount of time. Okay, before I discard it and I need to fetch in another block. If the cache is well designed, there is some amount of associativity, at least say 4-way associativity or so. If the cache is of reasonable size, etc., etc. Exactly the same concept is applied here. I do not want to go and search in the main memory for the page table because that is a slow operation. Okay, every address access, if I have to go and search in the main memory just to know the physical address, it is a quite unbearable overhead. Okay, so I must build a small cache-like structure which will mimic the page table inside the CPU chip itself. Such a cache which holds only a part of the page table, only the pages which are currently at play. Again, depending on the principle of locality, your entire address space will not be exercised at the same time. Please understand. This page table has 2 power 20 entries, no doubt, but your program will not need data or code spread over all the 2 power 20 virtual addresses. I mean, their entire virtual address span, 2 power 32 size virtual address span, all at one go. That is not the way normal human written programs work. Again, you apply the principle of locality and say, well, I cannot have a 2 power 20 sized hardware inside my CPU. That will be too large, but I will build a small cache. Maybe it will hold 256 entries or so, only 256 page table rows. And in that, I will hold some amount of translation information so that I do not need to go that often to the memory just to find the translation information. Most of the times I'll be happy with just looking in that cache and finding that subset information about the page. And I'll be happy that address translation will be performed by that fast cache-like memory, which is inside the CPU itself. Only when you do not find that information, yes, you have to go to main memory to fetch, consult the page table, get that information into the small cache-like memory on the CPU, get the page address, whatever. Okay, that small cache-like memory inside the CPU is called a translation look aside buffer, or TLB. Okay, that is an extension of the concept of cache, but only in the context of page tables. It does not hold, TLB is a specialized cache. It does not hold arbitrary program data or program binary. Remember, in modern CPUs, there are two caches. One is an instruction cache, and one is a data cache. The instruction cache holds only the program instructions, program binary instructions. Those also have to be brought from memory inside the CPU to be executed. Whereas the data cache holds the data which the program needs. The TLB is not an ordinary cache. It holds information which is a subset of only the page table, and we will come to it. First, let us study some more overhead bits that are necessary. Okay, so in engineering, you know, once you find that a concept is successful, you do not want to give away that concept that easily. Okay, you want to apply that concept in other contexts also. So the concept of cache memory is extended to the concept of this address translation mechanism also. Okay, so you would like to perform on-chip address translation using a faster cache like system called a TLB. Now, to reduce the page fault rate, again the LRU replacement scheme has to be used. Now, you first of all, LRU means least recently used. That as if means there is a concept of time of when this was last accessed, that has to be maintained. Maintaining time is very, very difficult. Okay. In fact, entire PhD thesis and books have been written of how to approximate the LRU algorithm practically in practical computers. Okay, and you will study some of those later on in your operating system course. There are some very clever schemes, some very strange schemes, etc. However, an extreme simplification of this is something called a reference bit. In a page table entry, other than the valid bit, you add another bit. You call it a reference bit. Whenever the page table entry corresponding to that is accessed, you set it to 1. Okay. So what does this mean? It means that now there is also a reference bit added here in the page table. If you look at the page table diagram, where some of them are 1, some of them are 0. The ones are the ones which have been touched recently. But periodically these bits are cleared to 0 by the operating system. All of them are cleared. Okay, why is this required? This is required because otherwise, you know, there is no distinction of time. I mean, how will you understand when have these been touched? Once it becomes 1, it will remain 1 forever. No concept of time is there, right? So when you have to choose between page replacement, okay, you have to look at the 1 or 0 bit. But if it is just sitting at 1, there is no concept of time. So periodically you just forget that memory that it was 1 for certain amount. Is periodically cleared by the operating system, and the page with reference bit 0 means it has not been used recently. So this is a kind of an page which is kind of ripe to be replaced. Okay. Now, what will happen to disk writes? First of all, if if you are performing writes to a disk, okay, the saving of data to a disk, suppose you are performing file operations, say in a C program, you have opened a file and you are performing write operations. The question is, every time you write something to the file, okay, using say something, what is a function for writing to a file, maybe something called footage or something, okay. Do you think immediately it gets updated on the disk? No, it does not, because small chunks of small writing operations to the disk, each of them take millions of clock cycles. So you rather wait. You write them to the update it on the memory page, okay, and periodically I mean when the file is getting closed or so, or when the file is getting closed and the program is exiting or something, you update it on the disk at one go. Write back policy. Write through policy is not practical in this game. Write through is immediately you sync it to the lower memory level, which in this case is the hard disk. That cannot be sustained, that is too slow. So you perform all updates into the memory page and then update it at one go at the lower level hard disk. So this uses the write back scheme, and this uses further another bit in the page table entry has to be added, which is the dirty bit. Earlier we have seen dirty bits in cache memories in write back to support write back schemes to show that this page has not yet been updated into the main memory. Now we are adding a dirty bit in the page table entry to show that this page has not yet been updated into the hard disk. Okay. So valid bit, dirty bit, reference bit. Now you have 3 additional bits per page table entry. Okay. So just notice how this is an extension of the concept of caches to the main memory and hard disk interface. Okay, exactly similar concepts, just in a slightly different manner is being presented. Okay. Now this TLB business. Okay, the address translation is quite slow, it seems, because every page table entry access requires one memory access. So this basically one memory access implies 2 memory accesses, which is quite disastrous. So you use a fast cache of page table entries within the CPU called a translation look aside buffer. How many entries are typically there? Well, typically it is between 16 to 512 page table entries. Usually it takes about 0.5 to 1 clock cycle for hit, which means if the hit happens, if the decision is made available within 1 clock cycle, 10 to 100 clock cycles if there is a miss, and the miss rate is typically between 0.01% to 1%. And the misses can be handled by hardware or software both. Now I have a question. Notice, look at the TLB. Now, other than the physical page address, the index is still virtual page number, no issues. Other than the physical page address, there is suddenly another tag field has come. There are valid dirty reference bits which are copies of the page table entries also. Suddenly one tag field has come. Why is that, may I ask? This physical page address, this is a copy of some page table entries. Why do we need a tag field with for every entry? That this tag field was not there in the page table actually. Suddenly here we find there are some tags. Why is this tag field there? What is the meaning of this tag field? First of all, how many TLBs are there? Page table is one per process, somewhere in memory. But how many TLB caches do you think are there inside your CPU? Only one. So TLB is a shared resource between different processes. Now, in this, taking cue from this fact, can you answer why is there a tag field?
Sir, to distinguish the processes.
Correct. So you need something to distinguish the processes. Okay. So there are physical page numbers can be, I mean, they can be the same. Accidentally, the same virtual page number can, I mean, you not accidentally, you look at virtual page number 10,000. Okay. Go to the TLB. Okay. So this is kind of a, well, this is a fully associative cache kind of a thing in a TLB. Okay, you find yes, my 10,000 virtual page number somewhere I am going. Okay, what is the what? And you find the physical page number, but for which process is that? That you have to figure out. So you need additional information. Okay. So the overall translation mechanism I want to show, then we will come back to this. This is the overall translation mechanism. Okay. First, you have a virtual address. I mean, this there is a virtual address is generated by the CPU. Okay. You search for the virtual page number. You all of them are searched in parallel. So this is a fully associative cache. Okay. Your virtual page number is matching. Then you find the corresponding physical page number and you calculate the page offset, and then your now the caching mechanism comes in. Okay, the caching mechanism has additional concepts called blocks. Notice here in this case, your page was of size 4 kilobyte, 2 power 12 bytes, whereas the block is only 2 power 4 bytes. Okay, 16 bytes. So there is a difference. Then there is a cache index. In this case, there are 256 cache entries. This looks to be a direct mapped cache to make life simple. And then you detect whether there is a cache hit or cache miss, or then you finally you get the you access the main memory and you get the data. If not access the main memory, if it is there in the cache, you can immediately return the data. Otherwise, there is a cache miss and all these things come out. The valid bit is checked in the TLB because that is important. Now, this concept of virtual page number address tag is slightly complicated. The problem of aliasing is still not resolved because the virtual page number is still, there is no mechanism to store, to kind of identify which process does this belong to. Okay, because there can be shared physical addresses but different virtual addresses also. So there are additional mechanisms that can be applied to have additional entries inside the TLBs to identify or resolve this type of aliases. However, we'll not go into it. And finally, another thing, this is a scheme which shows virtual address tags are being used. Okay, there is also an alternative. If the cache tags themselves, uh, oh no. This is the cache tags being using the physical address, and so translation happens before the cache lookup. Okay, so this is kind of more easily understandable. Now there is one problem. The problem is that if you look at this diagram, till now we have said cache lookup must be very fast, it must complete within one clock cycle, etc. etc. But if you look at this diagram, we find that before the cache lookup happens, first there is a TLB lookup. So now your hardware should be such that the combination of the TLB lookup and the cache lookup together takes one clock cycle if there is a cache hit and there is a TLB hit. Okay, so that is a quite quite difficult hardware design, isn't it? Because you are performing a TLB lookup if if you are getting the physical page number, you are then looking at the cache, and then you are if you are getting if this is a cache hit, you are returning the data. Everything should complete inside one clock cycle. The alternative used to use virtual address tags inside the cache, but then different virtual addresses for shared physical addresses are possible. There can be shared pages in memory, as I said. So those complications arise, and we'll not go into them. Even this scheme is also kind of is like substantially complicated. And I think here one of the inherent assumptions is that if you look at the TLB, other than the virtual page number, there is no process identifier. Okay, there is no process identifier as such. So I think this TLB content is essentially, it has to be refreshed for in a way for every process modification or every context switch, which makes sense because your page table itself is is process specific. There is no, like, every process will have a different page table itself. So your TLB, if it is a subset of the page table, so that must reflect that the process has changed. So that kind of overhead is also has to be somehow mitigated. Now, what happens if the TLB is missed? We have discussed what happens when the cache misses. Now, before cache, now this TLB, this animal has come in. So if there is a TLB miss, the page is not present. Page is if TLB miss indicates the not present. There are two possibilities. One is that the page is present, but the page table entry is not in the TLB, or the page is not present. Both are possible. Okay, and this misses must be identified, and the destination registers, before they are overwritten, they must be override, and exceptions must be read. Exceptions is a hardware generated interrupt kind of mechanism. Okay, so the internal hardware of the CPU themselves can inform the CPU that something bad has happened. Okay. For example, when we are discussing interrupts and exceptions, we discussed like say divide by 0. Divide by 0 is an exception. Okay. So invalid opcode is an exception. These are generated by the hardware units themselves. Okay. And the handler it copies the page table entry from the memory to the TLB and then restarts the instruction. However, if the page at all is not present in the main memory, then page fault occurs. So there are two different contexts of TLB misses. One is the page is present in main memory, but the page table is entry is not there in the TLB. That can happen. Entire TLB was searched and the page table entry was not found. Remember, this is a fully associative cache, so it can be anywhere. Okay, and the second is the page is not at all in main memory. Then the usual page fault mechanism has to kick in, and the operating system handles the pages, and it is, as I said, like tens of millions of cycles of penalty. How do you handle page faults? Well, again, you find the page table entry, you find the page on the disk, you have to choose the page to replace if there is not sufficient place on the memory. If the page that is to be replaced is dirty, it is written to the disk first. This is the write back policy, that don't replace something which is dirty directly. First copy it to the lower level of memory faithfully and then you replace it. Okay, then you read the page table in the memory and update the page table to show that currently that page which was missing is there in memory and it is hot, so the page table entry is updated, and then again resume the execution of the process, restarting from exactly the instruction which caused the page table fault, not from the beginning. Okay, so the process was evicted somewhere in between. Okay, now I would not go into this in detail. There is mainly two things to understand is that the hardware, there is some hardware, inbuilt hardware support inside the CPU. Okay, this is very important because you do not want to allow arbitrary user programs to perform arbitrary modifications to your memory. Okay, this is one fundamental way, and all the attacks, most of the attacks that you see, the operating system attacks, they basically want to somehow bypass the inbuilt protection mechanisms that are there implemented in hardware along with software. The CPU hardware understands two different modes of operation. One is called a privileged supervisor mode or a kernel mode. In that, certain operations are performed which no user program can ordinarily perform. Okay, so these user programs typically request in the form of something called system calls. Okay, for example, you have seen the syscall instruction. Okay, in x86 it is called the int or interrupt instruction. All these things, they invoke the supervisory mode and it asks the kernel, requests the kernel to do something on behalf of the user program. The kernel might listen to the request, it might not listen to the request. Okay. The page table and other state information. Okay, state in the context of a program or a process is the collection of registers in the CPU, maybe the stack, contents of the stack, contents of the registers. Okay, then another thing is probably the contents of the page tables. Okay, and the starting position of the page table for that process is held in the page table. There's some register inside the CPU which holds this page table registered. All of this together is the state of the process. So that state is only accessible in the kernel mode and not modifiable as such in general by an arbitrary user program. Okay. There are privileged instructions to so when it goes to the system call, it goes to the kernel mode, and then the hardware allows the execution of this privileged instructions. Of course, you can request something bad to the kernel, fool the kernel trusts you and tries to do things on your behalf which it should not have done, and you would harm the kernel. That is the way most attacks work. You intentionally want to do something which will fool the kernel into trusting a user program and take the system to a supervisory mode so that you can do anything you want. Okay. But there is some fundamental hardware techniques to prevent this. So as such, we have come to the end of our study of memory hierarchy. The common principle is caching. I will build a smaller, faster memory which will hold a subset of the stuff that is there in the lower, larger memory. I will work only with the subset, and most of the times I will be satisfied by only that small subset of data. Why? Because no real practical program uses the entire address space available for its data or code all at one go. Okay, that is not how real programs behave. There are some principles, practical principles of locality, spatial locality and temporal locality, and because of that, this concept of building small, faster memory, much smaller memory at a higher levels of hierarchy, closer to the processor, it works. Okay, so closer to the processor is a higher level of memory hierarchy. As you get down the memory hierarchy, the memory becomes larger. From cache, which is inside the processor, few megabytes at max, to main memory in ordinary computers, tens of or few gigabytes to tens of gigabytes, and finally to the permanent memory, non-volatile memory, which in current computers are either magnetic hard disks or non-volatile semiconductor memory in the form of flash memory. They are typically in modern personal computers in the order of small number of terabytes. On servers, etc., it can be much larger. At each level of the hierarchy, you have to think of where you have to take a decision, where you have to place a block, how you will find the block very fast, what will you do if a miss happens and you have to replace something, okay, and what will be your write policy. That is, when you are performing a write at certain memory hierarchy, how would that write be synchronized at a lower level of memory hierarchy. All of these are extremely important issues which have to be considered individually and decisions have to be taken. For block placement in caches is a huge issue for which we have seen several schemes. We saw schemes where there is no flexibility of where a block can be placed, which is a direct mapped cache, up to a scheme where there is full flexibility of where a block can be placed, which is a fully associative cache. However, both of them are impractical. Direct mapped cache is impractical because it is extremely inefficient with respect to the hit miss behavior. Fully associative cache as such is attractive the class আছে আমি একটু পরে কল করছি দেখো fully associative cache is very flexible. You can place any block you like anywhere in the cache. However, it is difficult to build hardware to perform parallel search over an entire cache. Large cache, so fully associative caches are really small. But if you make a cache very small, then capacity misses can happen. So you rather go for a trade-off and you go for something called set associative caches, which is somewhere in between direct mapped and fully associative cache. And you give some amount of liberty to the blocks to go and sit in the cache, but not full liberty. Okay. Finally, you come to the interface between main memory and hard disk. Modern computers, through a mechanism called virtual memory, which is supported both by the memory management hardware built inside the CPU as well as the operating system kernel, it gives an impression or kind of creates an illusion to the application programmers that every application program has the entire address space starting from 0 up to, if it is a 32 address space, 2 power 32 minus 1, this address space is available logically to it. However, naturally, you do not have that much of memory. Even for one single process, you do not have that much of memory. Forget about multiple processes. So in physical in physical reality, there has to be a translation from these virtual addresses to physical addresses. Typically, you do not get to know what are the physical addresses. This information is hidden from the users, and most of the times we deal only what addresses we deal with. Those are basically virtual addresses. Now there should be a virtual address translation mechanism from virtual to physical address. The virtual address translation mechanisms employs a translation table called a page table. The chunks of data when we are dealing with virtual addresses are called pages. These pages typically are several kilobytes to several megabytes in size. Modern CPUs and operating system support multiple page sizes for at the same time. Now, just in time when application needs a data, the operating system makes the page ready for it through some prediction mechanism and some intelligent page replacement policies, so that the user of the application do not feel any what should I say, any problem in executing the application. Okay, well, there can be some latencies. I gave an example once that suppose you are watching a movie and you suddenly move the slider to the end of the movie. You might find there is some latency because the entire movie is probably not there into your main memory. So if you had watched serially, there would be no stop and your entire movie will play without any interruption. However, if you suddenly move to the end, then again suddenly move to the front, depending on whether the pages corresponding to the movie file, all the pages are there in your main memory or not, you might find some latency. Okay. The first time you invoke a software, suppose you have, say, Microsoft Word. There is an icon on the desktop, you double click on it. It takes some time to invoke. Why? Because that software has not been loaded into memory from hard disk. Okay, there are some operating systems which gives an option that you can select some software which, when the operating system will be booting, okay, when you turn on your computer, those software, the necessary software will be loaded into the main memory. Would the entire software be loaded? Probably not, but at least the pages of that software which will allow you to invoke the software quickly, because those are in main memory. Okay, rather than in the hard disk. You can select this software. I know Mac OS X allows it. I think Windows also allows it. Linux, I'm not sure. Maybe Linux also allows it. Now, it is very important that the pages of certain processes are there in main memory as much as possible, because if it is not, something called page fault happens. And page fault is a horrible scenario where there are millions or to tens of millions, that is crores of clock cycle penalty in fetching the chunk of data, that is the page, from the hard disk to the main memory. However, when the main memory is used as a cache in the context of a virtual memory mechanism, generally fully associative placement is allowed, so that any page can come in with any virtual address, can come in and sit anywhere. Which means that now if you have a cache inside CPU, a fast cache, which will associative translation look aside buffer or TLB, it can sit above before the caching mechanism and perform the translation, and the cache can itself take the page table entry, and either it will find the data, it will not find the data. The TLB itself, either there can be two types of TLB misses, that the data is there in main memory, but it is not there in the TLB, the translation data. So that is a less severe error, TLB miss. But it might happen the page at all is not there in the main memory itself. That is a page fault. So that, as I said, is serious error, and process which has undergone a page fault is typically evicted from the processor and sent in a wait state, and it waits till the page has been brought from hard disk to the main memory, and then it starts executing again after some time. Okay, that's why if a page fault happens, you typically find a delay in the response time of the application that you are working with. And also there is always an initial latency for any application which you invoke. As I said, if the application is substantially complicated, like say something like a full-fledged word processing software, or something like a presentation software like PowerPoint or something, well, it will take time. Okay, so that's more or less it. Details of the virtual memory translation, how page tables are stored, what are the efficient data structures to store. The page table data structure which is shown in this type of diagrams are logically correct, but physically impractical, because the page table sizes for each process will become too large. So there are ways to kind of design more compact page tables, which in the operating system course you will learn. You will learn protection mechanisms of how logical address spaces of one process is protected from the logical address space of another process, etc., etc. Okay, so that's more or less it. I would stop today's class here. On Thursday's class, I will again go through the exception, this interrupt mechanism, and now we have discussed page faults. I will again go back to the how are page faults handled, how are interrupts handled in general, what are the types of interrupts, what are the differences of interrupts with exceptions. A modern computer is interrupt driven. Okay, continuously interrupts keep happening and the CPU handles them. How does that work? How does the operating system help? What is an interrupt vector table? What are the different process states, etc., etc. All of these details we will study in Thursday's class. And Thursday's class would probably be the last class that I will teach in this semester in the theory portion for you, because from next week, Professor Bhargav Bhattacharya will again take over and he will be teaching the processor pipelining portion. Okay, there will be another exam. We will inform you about the exam in due course. Okay, it will be there. It will happen during the exam week. Okay, so that's it. Thank you, students. I'll now stop the recording.